Welcome back to this chapter, gases. Last lesson, we learned what are the variables that explain the characteristics and behavior of gases. And in this lesson, we will talk about how these variables are related. Let's see the relation between the pressure and volume. We can demonstrate like this. When you take a syringe closed at the nozzle, and when you push in the plunger, you can see the volume is decreasing and the pressure is increasing. That is making that marshmallows shrink. And when you pull the plunger out, the pressure is decreasing and the volume will increase. So as you can see here, so you can even try that one with a syringe with just air. You can feel the pressure when you decrease the volume by pushing the plunger in. So now you can see the science behind it, the number of particles, or you can see the space between the particles is getting smaller when you apply more pressure. So the volume decrease when more pressure, or I can say when pressure increase. And the temperature is remaining same here, and the number of moles are also remaining same here. So those two variables remain same, only we are talking about the relation between pressure and volume. So both are related inversely, in direct proportion. When the pressure increase, volume decrease, and when the pressure decrease, by pulling the plunger out, the pressure decreases and the volume is increasing. So that is the relation between pressure and volume when the temperature is constant and the number of moles also remain constant. You can easily remember this relation by taking a meter stick or a ruler and write them in alphabetic order: pressure, temperature, and volume. And when the temperature remain constant, and keep that, hold at the center and put the pressure part down, and then you can see that volume is increasing, and vice versa. So when you put that pressure part up, you can see the volume is decreasing. That is just a memory tip. So the pressure and volume are inversely proportional. This relation is explained by the scientist Boyle, and this is called Boyle's law. So the relation between pressure and volume, inversely proportional. So P is proportional to 1 over V. That's the way we show the inverse proportion. And then pressure equal K times 1 over V. So that is when proportionality sign changes to equal to sign, we will write a constant K. And when you plot it as a graph, you can see that pressure and volume is not directly proportional. But volume and inverse of pressure, or vice versa, pressure and inverse of volume will be direct proportion, and we will get a linear graph. And if you compare two samples, we can see that pressure times volume of the first sample equal pressure and volume of the second sample. So when you alter that one, so this is the famous equation we are using to solve the Boyle's law problems. So remember, this is at constant temperature, and we are considering the number of moles is same for all the other gas laws as well. So the second one is the relation between temperature and volume. So when the temperature increases, volume is also increasing. So this is direct relationship, not like pressure and volume. So we are getting volume versus temperature graph as linear. So again, V1 over T1. So when you take that volume to the left side, temperature over volume is a constant, or temperature to this side, volume over temperature is a constant. So that is same. So V1 over T1 equal V2 over T2 is the relation for comparing two gases of the same pressure. So here the pressure is constant. So that relation, that's the formula we will be using. In this one also you can find in your reference material. And the other law is Gay-Lussac's law, which is the relation between pressure and temperature. Pressure and temperature are directly proportional at constant volume. So when you take that into constant terms like this. Pressure over temperature is a constant K. So when you compare two gas samples at the same volume, pressure over temperature of the first one equal pressure over temperature for the second one, and you will get a linear graph when you plot it in the graph. So pressure versus time will be a linear graph. And the last one is, now if the pressure and temperature remain constant, the volume and number of moles are related directly. So when the volume increases, the number of moles increases, and vice versa. So when you plot a graph between volume and number of moles, we will get a linear graph. So when the balloon, for example, when you blow up a balloon, in the beginning it will be small. So when you add more and more air into it, that means you are introducing more moles of air, and the balloon will become bigger. So volume and number of moles are directly proportional. Now we can combine all the four gas laws we have just discussed. So we will get a relation which is called combined gas law. We will get a relation P1 V1 divided by N1 T1, which equal P2 V2 divided by N2 T2. So for example, if you want to look at only the Boyle's law, the number of moles and the temperature remain constant, so we don't have to consider the denominator, and we will get P1 V1 equal P2 V2. And for the Charles law, we can take the variables P1 and N1 remain same, and then V1 over T1 equal V2 over T2. So we don't have to consider P1 and N1 for Charles law. And for Gay-Lussac's law, we don't have to consider V1 and N1 or V2 and N2. We can take that one off from this one, and then P1 over T1 equal P2 over T2. So for Avogadro's law, we have pressure and temperature constant. So V1 over N1 equal V2 over N2. So that is called combined gas law. So if you can just remember this one, we can actually derive everything separate from this combined gas law.